Our next up, we have dissociation equations. Be careful with these. This is not a type of chemical reaction. So a dissociation equation shows what happens when you put usually an ionic substance in water. So it says the process of dissociation occurs when an ionic solid dissolves in water, forming an aqueous solution. So that word dissociate means to break apart into ions. And I'll show you some examples of this in a bit. So remember, in an ionic compound, those cations and anions are stuck together. And when you put that in water, what happens is the water molecules actually pull the ions apart from each other. You end up with individual ions. That process is known as dissociation. So just to review some terminology, substances that are able to dissolve in water are called soluble. So only soluble ionic compounds will dissociate. And if a substance does not dissolve in water, we say that it is insoluble. Insoluble substances do not dissociate in water. Well, not at least until second semester. Before we do the actual examples that are in the notes, let's start off with something simple. I want to show you an animation of this later. Let's say we took sodium chloride. First of all, sodium chloride is a solid. What would happen if we were to put it in? What would happen if we were to put it in water? Let's write the dissociation equation for sodium chloride. Let's show what happens when you put sodium chloride in water. So what we want to do is we want to start with solid sodium chloride on the left side of the equation. Now the sodium chloride is not reacting with water, so it's just the water is going to help to dissolve it and dissociate it. So never, ever, ever put water in a dissociation equation. Again, this is not a chemical reaction. So we'll start with the ionic solid on the left side, and then on the right side we're going to put the aqueous ion. So sodium chloride is going to separate into its ions. So I didn't use that term exactly like that before. Dissociate means to separate into its ions. Now what are the ions that make up this compound? They are sodium ions and chloride ions. We're going to show that on the right side. So sodium has a charge of +1, chloride has a charge of -1. Again, if it's an ion, make sure to include its charge. Notice the state of matter I put there. I put aqueous, AQ. AQ means dissolved in water. In fact, the only place that we find ions are in solution. I'll actually show you an example of a solution in just a bit. All right, let's take a look at some more examples. Write the balance equation for the dissolving of magnesium nitrate in water. Show what happens when you add magnesium nitrate to water. First of all, is magnesium nitrate soluble? Because if it's not soluble, then we're not going to write a dissociation equation. It won't dissociate. So make sure you're familiar with the solubility rules. All nitrates are soluble, so magnesium nitrate is soluble. It will dissolve, and if it does dissolve, in this case, it will dissociate. So go ahead and pause the video, write the balance equation for the dissolving of magnesium nitrate. Pause now, please. So we want to make sure our equation is balanced. We have 2 nitrates on the left, so we want to make sure we have 2 nitrates on the right. Again, don't forget about those charges. Magnesium nitrate will dissociate into magnesium ions, Mg+2, and nitrate ions, NO3-. And take a look at the ratio of the nitrate ions to the magnesium ions. I'll show you a demonstration of this in a bit. So let's see what happens with something like sodium chloride. So chemical formula for sodium chloride is NaCl. And so what I'm going to do is I'm going to shake some of this and put that in the water, and we'll see what happens to the sodium chloride. So shake a little bit out. I paused it so you can see. Green represents the chloride ions, and pink represents the sodium ions. And notice that before they hit the water, they're all stuck together in that crystal lattice. So let's see what happens when they hit the water. Animation's a little slow this morning, it looks like. There we go. Look at that. All all the ions separate from each other. So they dissociate. And so what I'm going to do is I'm going to pause the video, or pause the animation rather, and I want you to count all of these sodium ions. So that is in pink, and count all the chloride ions. So let's see if I count all of these. Count the green ones first. 933. All right, looks like there are 173 chloride ions. Let's count the sodium ions now. 173. So what do you notice? For every one sodium ion, there is one chloride ion. And so that's what we show in our dissociation equation. For every 1 mole of NaCl formula units, we produce 1 mole of sodium ion and 1 mole of chloride ion. So for every 1 formula unit, we have 1 Na plus and 1 Cl minus. So what if we have something like magnesium nitrate? So in magnesium nitrate, the charge of the cation is +2. We see that indicated that up here. And then the anion is -1. Again, let's shake it out, see what happens. This time we have black are the magnesium ions, white are the nitrate ions. So all stuck together initially. When it hits the water, let's see what happens. Again, we see that the ions separate from one another. That's called dissociate. Let's pause the video, count them up. All right, so we can just see, just by looking, we see that there's more whites than black. Remember, whites are the anions. There's more anions than cations in this solution. So if we count up the cations, there happens to be 61. And if we count the whites, the anions, we see that there are 122. So what do you notice? There are twice as many anions as there are cations in this solution. And isn't that what you saw in your balanced dissociation equation? So that's what happens when a soluble ionic compound is placed in water. It will dissociate, meaning those ions that were initially stuck together will break apart from one another in a process called, again, dissociation. Go ahead and try this one out next. Write the balanced equation for the dissolving of ammonium carbonate in water. Again, make sure it is soluble before you write the equation. Make sure the equation is balanced. Make sure you have take the matter. Go ahead and pause the video and work on that. Ammonium carbonate is going to dissociate into ammonium ions and carbonate ions. Again, take a look at the ratio of the ammonium ions to the carbonate ions. This will be important later on. All right, let's try another one. Again, pause the video, write the balanced equation for the dissolving of potassium bromide in water. Pause now, please. So something we didn't talk about with our very first example, I'll talk about now. Notice bromide. It's not that you're making bromine. Bromine is Br2. You're not making potassium metal and liquid bromine. You're making ions. So we don't use hot sprinkle with dissociation equations. We're not making bromine. We're not making chlorine. We're making bromide ions. We're making chloride. We're not really making. They're just separating it from the cation to form a solution. So no, ever, no hot sprinkle in dissociation equation. All right, one more. Write the balanced equation for dissolving strontium sulfate in water. Make sure to pause the video and work on that now. All right, hopefully you did not write that this dissociates into strontium ions and sulfate ions. If it were soluble, that's what you would make. But this substance is not soluble. So when you put strontium sulfate in water, it does not dissolve. And so if it does not dissolve, it most certainly will not dissociate. Now, some of you might be thinking, how do you know that strontium sulfate is not soluble in water? Solubility rules. So make sure to memorize the solubility rules, not only for these dissociation equations, but for the double replacement equations as well, where we're predicting if a precipitate will form, what that precipitate is. All right, next up, ionic and net ionic equations. So again, it says ionic solids that are soluble in water are dissociated. So when we write ionic equations, and I'll show you examples in a bit. When you write an ionic equation and a net ionic equation for a reaction, anything that is shown in solution, anything that is an aqueous ionic compound, will be shown dissociated instead of together. So let's say you had aqueous sodium chloride. In your ionic equation, you're going to not write NaCl, you're going to write Na plus and Cl minus separate from each other. So all aqueous ionic compounds are shown dissociated in ionic and net ionic equations. Let's take a look at this example. It says, write the balanced net ionic equation, we'll get to that part in a bit, for the reaction that occurs between solutions of cobalt nitrate and sodium hydroxide. I'm actually going to show you this reaction. So the first thing I want to do is I need to make a solution of cobalt 2 nitrate. So let me show you what that looks like. So here's our cobalt 2 nitrate. You can hear it. Notice that it is a solid. So this is called a scoop. So we use scoops anytime we're going to transfer solids from one container to another, from measuring out any solid. In this case, I want to make a solution. So I'm going to put just a very small amount of the cobalt 2 nitrate in this test tube. Let me scoop some out. I'll show you what it looks like. So there's our cobalt 2 nitrate. It is a red solid. Hopefully you can see that okay. I don't know what the best view is. So now notice in the original problem I said we're going to write the balanced equation for the reaction between solutions of cobalt 2 nitrate and sodium hydroxide. So I need to make a solution out of it. So what I'm going to do is I'm going to dissolve this. I'm going to add some deionized water. So you have a water bottle at your lab station. For those of you that will be joining us in person, this is deionized water. Deionized water is water without ions. So sometimes the ions in tap water can cause precipitate to form when you're trying to make a solution, and we don't want any precipitate to form. And so we're going to use deionized water. So I'm going to add some to my solid. I don't care too much about the concentration of this solution. I'm not trying to make a specific concentration, so I just add an arbitrary amount of water. Now, you might be able to see there is still solid on the bottom of the test tube. So I want to dissolve the solid. So the procedure we use for dissolving solids in solution in the test tube is hold it really tight, and then I'm going to pass my finger kind of at an angle, diagonal, down through the bottom of the test tube. Don't just tap it. Certainly don't flick it. I'm going to pass it through. I'm going to create a vortex inside of the test tube. I don't know if you can see that. Got that stuff spinning around in there. You get all that solid to dissolve. Okay? And there is our solution. Anytime you're recording observations of solutions in the laboratory, make sure to include both its color and its clarity. So the color is kind of red, maybe pink if you want to put that, that's fine. Clarity, either you can see through it or you cannot. If you can see through it, we say it is clear. If you cannot see through it, then it is opaque. So this solution is red and clear. So to that solution, I'm going to add some sodium hydroxide, a solution of sodium hydroxide. So sodium hydroxide by itself is a solid. I've taken that solid, dissolved it in water to make a solution. This bottle is kind of opaque, but the solution inside of it is colorless. So if it has no color, please don't say white. It is colorless, and it is clear. So I'm going to add that to my solution. Now again, think about what's in here. What's in a solution of cobalt 2 nitrate besides the water? Is there any cobalt 2 nitrate in the solution? Think about what we just said about soluble soluble ionic compound. Likewise, in this solution, what exactly is in here besides the water? Is there any sodium hydroxide in here? No. Sodium hydroxide is a soluble ionic compound. There's no NaOH in here. Okay, think about that for when we write our ionic and net ionic equation. So now I'm going to add a few drops of the sodium hydroxide to the cobalt-2 nitrate, and we'll see what happens. See if I can get that into use here. Hopefully you can see that okay. Try to get out of the way here. So we see we got solution still there, but we got this blue substance. Actually, I don't know if you can tell. That blue substance is a precipitate. So this is a double replacement reaction that produces a precipitate. So again, we want to be thinking about what's in here when we write our balanced equation. Let's go ahead and do that. Let's write the balanced double replacement equation for the reaction. I'll let you do that. Go ahead and pause the video now. So here's our balanced equation. Make sure to include states that matter. So notice that the cobalt-2 nitrate is aqueous. I had a solution of that substance. And the sodium hydroxide, also aqueous. Double replacement reaction. The cobalt-2 and sodium ions trade places. You end up with products of sodium nitrate and I want to say cobalt hydroxide. What is that? That is cobalt-2 hydroxide. So remember, charges of the ions do not change during a double replacement reaction. So sodium nitrate, cobalt-2 hydroxide. Which one of those was that blue precipitate? Well, all nitrates are soluble. All alkali compounds, alkali metal compounds like sodium compounds are soluble. So definitely sodium nitrate is soluble in water. Most hydroxides are insoluble. There are some exceptions. Cobalt-2 is not one of those exceptions. So that precipitate was cobalt-2 hydroxide. All right, let's take a look now at the ionic equation. Before I change the screen, again, look at everything that is in solution. In our ionic equation, everything that is in solution is shown dissociated. Let's go ahead and write that together. Let's start off with the cobalt-2 nitrate. What exactly was in that cobalt-2 nitrate solution besides the water? Two things. Cobalt-2 ions and nitrate ions. So let's write that. Now, I'll worry about balancing at the end. There's a couple different ways of balancing this equation. I'll explain that later. Next, sodium hydroxide. What exactly was in that solution besides the water? Two things. Sodium ions and hydroxide ions. So let's write this. On the right there, we got sodium nitrate, aqueous sodium nitrate. So we have that solution there in the bottom of the test tube. What exactly is in a solution of sodium nitrate besides the water? Again, two things. Sodium ions and nitrate ions. Now, what do you notice about the cobalt-2 hydroxide? Is it aqueous? Is it soluble in water? So things that are soluble in water, we show them dissociated, separated as ions. Things that are insoluble in water, meaning they don't dissolve. If they don't dissolve, they don't dissociate. So those insoluble substances in our ionic equation, we're going to show what's the opposite of dissociated? I guess it would be associated together. We're going to write that precipitate as just the same way as it was in our original equation. So to make sure this equation is balanced, you can balance from the original equation if you want, or you can just balance at the end. If we balance from the original equation, we need a 2 in front of nitrate on the left side because it was cobalt 2 nitrate. We need a 2 in front of Na plus because there were 2 NaOHs, a 2 in front of OH minus, a 2 in front of Na plus on the right, and a 2 in front of NO3 minus on the right. I'm just going to balance from this equation. So the only thing we need to balance is hydroxide here. 2 hydroxides on the right, so I need 2 on the left. Alright, so that is our balanced ionic equation, which is called. Everything that's in solution is shown dissociated. Let's take it one step further, and let's write the net ionic equation. So notice in our ionic equation, we have substances that are the same on the left side as they are on the right side. Same thing. Now, NO3 minus on the left. We have NO3 minus on the right. Likewise, we have Na plus on the left and Na plus on the right. And so in our net ionic equation, anything that doesn't change, we're going to eliminate. So what doesn't change? NO3 minus doesn't change, Na plus doesn't change. We're not going to show that in the equation. The things that do change, we are going to include. So in this case, our net ionic equation shows the 2 ions that combine to form the precipitate. So we have 2 ions on the left. On the right side is always going to be our precipitate. All right, so those ions that didn't do anything, those ions that were present after the reaction as well as before the reaction, are called spectator ions. They're called spectators because they don't do anything. They're just watching the reaction. So we're going to get rid of, as we saw in our last example, the spectator ions. So what were the spectator ions in that reaction between cobalt 2 nitrate and sodium hydroxide? We have 2 of them. Usually always going to have 2 spectator ions in a double replacement reaction. So in that reaction, our 2 spectator ions were sodium ions and nitrate ions. In fact, because all sodium compounds are soluble and all nitrates are soluble, sodium will always be a spectator ion, and nitrate will also always be a spectator ion. All right, it's your turn. Go ahead and write the balanced double replacement equation, the ionic equation, and the net ionic equation for this reaction. Solutions. So we'll say that both solutions of sodium phosphate and lead 2 acetate are mixed. Go ahead and pause the video, write those 3 equations. Once again, it's really important to know your solubility rules. If you don't, you're going to get the wrong precipitate, and your ionic and net ionic equations are going to be wrong as well. So in this reaction, we produced a precipitate of lead 2 phosphate. There's our balanced double replacement equation. Ionic equation, everything that is aqueous is shown dissociated. Our precipitate is shown associated. Spectator ions, we got sodium ions and acetate ions. And so we're left there with our net ionic equation. It doesn't really matter what order you put the ions on the left side. I'll just put the cation first. But if you want to just put phosphate first, because it's written first in the ionic equation, that's okay. Make sure that equation is balanced. And let's go ahead and try one more. Write the balanced double replacement equation, ionic equation, net ionic equation for the reaction between solutions of aluminum chloride and potassium hydroxide. Go ahead and pause the video and work on that. And there are the 3 equations for this reaction. That concludes this lesson. Please let me know if you have any questions. We'll be sure to do some more examples if we need to. Thanks for watching.